In section 4.3, we generalized what we did in 4.2 and introduced the idea of a definite integral. So first of all, let's generalize this idea of a Riemann sum. Let's say that we have a function defined on an interval from a to b, and we want to approximate the area underneath the curve. Now in the previous section, we divided this region up into equally spaced intervals so that we had rectangles of equal width. But notice that if the function is increasing fast for a while, levels off, and maybe increases fast, then that's not going to be the most efficient way to estimate the area. In fact, here where the function is relatively flat, we could take one fairly big rectangle like this. But the places where the function was increasing relatively quickly, maybe we would take more rectangles there. So maybe the places where the function is changing, we put more rectangles. The places where the function is relatively constant, we use fewer. So we might split things up a little bit more like this. And there's certainly ways, if you're doing this using computers, that you can program the computer to split it up in such a way. So some of the intervals might be wide, some of the intervals might be narrower. So first of all, let's see how we could indicate what the endpoints of these are. I can let x naught be my left endpoint, and then number the endpoints from there, x1, x2, x3, x4, and so on, where b is going to be my last endpoint. This list of numbers, x naught to xn, is called a partition of the interval from a to b. So our first step is to choose a partition x naught, x1, x2, all the way up to x sub n. So this is an increasing sequence where x naught is my left endpoint A and x sub n is my right endpoint B. Now notice that these rectangles might have different widths. So I'll say that the width of r sub I is called delta x sub I. Previously, when they all had the same width, we just said delta x. If they have different widths, I'll indicate it by saying delta x sub I. And notice the formula for that is going to be the right endpoint minus the left endpoint. So since the right endpoint of r sub I is x sub I, the formula for delta x sub I is x sub I minus the previous one, which is x sub I minus 1. So the width of R4 is delta x sub 4, which is x4 minus x3. So that's what we use for the width. Now for the height, previously we've been using the right endpoints. So for example, for R2, we would have cut things off using the right endpoint like this. Well again, that might not be optimal. Notice that that right endpoint approximation in this picture would have all of this extra space. Whereas maybe if we chose a point in between, the area of the rectangle might be closer to the area under the curve. So let me expand that picture a little bit. If this is r sub I, it's going between x sub I minus 1 and x sub I, and it has a curved top like this, then we certainly could use a right endpoint or a left endpoint, but we can also choose any point in between and use that to determine the height. So this point in between, we're going to call c sub I. And we'll get the height of r sub I by substituting c sub I into the function. So the height of r sub I will be f of c sub I where c sub I is some point we've chosen between x sub I minus 1 or x sub I. So it could be the left endpoint or the right endpoint, or it might be the midpoint or any other point in between. Again, we're trying to make things as flexible as possible. From here, things will look familiar. The area of R sub I will be the height times the width. The height was f of c sub I, and the width was delta x sub I. So the total area of all n rectangles is going to be the sum I equals 1 to n of f of c sub I delta x sub I. So the two things we've done to generalize a little bit is we're no longer assuming that all the rectangles have to have the same width, and we're also allowing ourselves flexibility in choosing the right endpoint, the left endpoint, or any point in between to determine the height. And this is the general form of a Riemann sum. Now, the next step in calculating areas previously was to let n go to infinity. But the idea behind letting n go to infinity was that we wanted to make all of our rectangles skinnier and skinnier. So we need to make an extra definition here to talk about how we can control the width of all the rectangles at once. So let's go back to the partition. Remember, the partition was just a set of numbers between A and B, increasing from left to right, and we said that the width of each rectangle was delta x sub I. So notice that the widest rectangle is going to be the one that has the largest delta x sub I. So let's capture that, and let's define the mesh size which we'll call magnitude of delta, to be the maximum of all the delta x sub i's. So the mesh size is the width of the widest rectangle. So obviously in this picture, that's going to be R sub 4. And then here, when I say that I want to make all the rectangles skinnier and skinnier, we'll take the limit as the mesh size goes to 0. Because if the biggest rectangle has a width that's going to 0, then that means that every smaller rectangle has to have a width that's going to 0 as well. And now with all of that, we can write down our formula for the area. Their area will now be the limit as the mesh size goes to 0 of the Riemann sum, sum f of c sub I times delta x sub I, sum I equals 1 to n. And this is known as the definition of the definite integral. So if this limit converges, no matter what partition you use, and no matter what point ci you use, and you get the same answer no matter which way, no matter what partition or what ci's, and that's known as the definite integral. And it turns out that if the function is continuous, then this limit will exist. And the notation is this: integral of f of x dx from a to b. So the f is the function under which you want to find the area, and the a and the b are the endpoints of the interval.